Hello, everyone. I'm Bhargav from Web3 Foundation. I'll be talking about the security analysis of the Polkadot Ethereum bridge, which is going to go live pretty soon. So this analysis was performed at the Web3 Foundation with lots of inputs from devs at Parity and Snowbridge, and also external auditors. So let's get started. I know this is the builder space, but just so that we are all at the right level of abstraction, what are bridges, right? So as in the physical world, bridges help connect two siloed regions. That's exactly the same even in the blockchain world. So it helps, it's like a piece of infrastructure which facilitates interoperability between independent, technically diverse chains, right? So like Polkadot and Ethereum, they have like different consensus mechanisms, different layers of networking and so on. So it's hard for one chain to listen to the other chain or communicate with the other chain. And these are exactly what bridges are for, right? So the chains, like bridges allow the chains to fetch and believe the state of the other chain. So for example, over here, Polkadot has some latest state, Ethereum has some latest state, and with the bridge, you would be able to fetch and believe the state on the other chain. And for this talk, we are really looking at this layer of abstraction here. And there can be like interesting applications that can be built on top of this basic functionality, right? So be it like asset transfers, like migration of the state trie from one chain to the other, games, it can all be built on top of this basic layer. So traditionally, bridges use trusted intermediaries, right? So what I mean by trusted intermediaries is that you usually have like a trusted relayer who runs both the nodes on both like the source and target chains. And yeah, the two chains trust this intermediary, which is usually a multi-sig, to listen to the other chain, right? But this obviously has a lot of cons. The first thing is that you have extra trust assumptions. Now, the security of the bridge relies on how reliable this intermediary relayer is. And it's centralized, right? So it's like a single point of failure if this relayer snaps. So, and this can cause like both safety issues, that is, the intermediary can send in like malicious state from one chain to the other, or liveness, like he like censors some messages which are in one chain and doesn't pass it on to the other, right? So, and this approach is so far not so good, right? It's common knowledge that multi-sig bridges are extremely vulnerable to attacks, and the main point is that there is like a single point of failure, right? So a number of attacks have been surfaced over the last few years. This is like a tweet about like the Orbit bridge being hacked, then the Harmony bridge, then this one is about like the Ronin bridge. And if you see, like there have been studies which estimate that more than half of all the blockchain hacks are related somehow or the other to bridges. And this brings back to the like a phrase in security which says that like security is as strong as its weakest link, right? And clearly, trusted bridges are that weak link. So we don't want to go this trusted route, but have like a trustless bridge, right? So let's define what trustless means here. Obviously, we still have to trust some things, right? So by trustless, what I mean is that there is no additional trust assumption on the intermediary relayers for the safety of the bridge. So we still have the trust assumptions, like the BFT kind of trust assumptions on both the chains, but we don't have any extra assumptions, right? And this kind of leads us to a few requirements, and like the requirements are that anyone can run a relayer, right? So there need not be any stake or deposit that the relayer has to deposit before becoming a relayer. This is like one of the crucial requirements for us. And any misbehavior that is traceable, any misbehavior that is detected is finally traceable to the validators, right? Because they are the ones who have the stake, and they are the ones who need to be punished. So in other words, it's like we don't want to shoot the messenger, right? So the relayers are just relaying the message from one chain to other. But if something goes wrong, we need to catch hold of the validators who initiated this malicious behavior. So, like, the obvious approach for this is to use light clients, right? What I call like the light client approach. And here, it's pretty simple, right? So for the instance of Polkadot Ethereum bridge, what we do is we run an Ethereum light client as a parachain on Polkadot, and this listens to the finality on Ethereum via the Altair protocol or like through sync committees. And for the other direction, we just run a Polkadot light client as a smart contract on Ethereum, and this listens to Polkadot's finality, right? So if we embed light clients within both of these chains, then they will be able to trustlessly listen to the other chain. Right? And basically, we then need these trustless relayers just to relay the messages between the chains and collect fees during the process, right? For the effort that they put in sending the messages. So let's look at both the directions, right? So let's look at the Ethereum to Polkadot direction. That is, Polkadot wants to listen to the finality that's happening on Ethereum, right? So Ethereum has this light client protocol called, which is based on sync committees. So it randomly selects 512 validators out of the 500,000 validators to sign the block, right? And we run a Ethereum light client as a parachain on Polkadot, right? So this is really the easier direction because Polkadot is efficient and it's compatible with this light client protocol. The more interesting direction is actually the other way around, right? We want to make Ethereum listen to the finality on Polkadot. And since Ethereum is not the most efficient of chains, this brings in a lot of challenges, right? So yeah, basically the question is like, you want to run a light client smart contract on Ethereum, which is very expensive. So how do we efficiently do it and make it listen to the finality on Polkadot, right? And here comes Beefy, right? So the way I look at it, Beefy has two components. One of them is a secondary layer of finality on Polkadot itself. So this is basically an additional layer of finality on top of Grandpa, which just makes it easier for Ethereum and other on-chain light clients to follow it, right? So making it more compatible for Ethereum to follow the finality. And the other component is actually this random sampling technique. It's basically an interactive protocol which reduces the costs of running the bridge while still retaining security, right? And the rest of the talk is going to focus on this random sampling technique on how Ethereum listens to Polkadot's finality, right? So I'll try to explain the protocol in a very high level. I'm obviously omitting a lot of details here through something called like message sequence charts, right? So you can think of Polkadot as like one of the actors, the light client on Ethereum, the smart contract as the other actor, kind of abstracting some things out. But let's look at, before like the optimized version, let's just look at the baseline protocol, right? So how would a smart contract on Ethereum listen to Polkadot finality, right? So once a block is finalized, so let's assume there are like 3f+1 validators on Polkadot, where at most f can be malicious, like the usual BFT assumptions. So a Beefy block is finalized when like 2f+1 validators sign on that block, right? So the simple thing that we could do is send all these signatures to the smart contract, and then the smart contract verifies all these 2f+1 signatures, right? But the obvious drawback here is that this is going to be super expensive because, yeah, I mean, there are like transaction costs and gas costs that the smart contract has to pay for verifying all these 2f+1 signatures, right? And in Polkadot, we are talking about like more than 200 signatures here because like there are 300 validators. And on Kusama, this is like even larger. So now let's look at like a slightly or like a more optimized version of this protocol, right? So the key idea or insight here, this somehow we use randomness to reduce this costs on Ethereum, right? So let's look at the interactive random sampling protocol, which is like the optimized version, right? So we have, again, a, a block is BFI finalized when it has 2f plus 1 validator signing on it. But now, instead of sending all those signatures and getting it verified on the smart contract, what the relayer claims is that it claims that it has 2f plus 1 signatures. So it claims that I have got those signatures, but it really doesn't send them all, right? So it just claims that it has like 200 signatures on Polkadot, which signed on the BFI finalized block. And what happens is now the light clients get to know, okay, you claim that you have these 200 signatures. What I will do is I will use a source of randomness. Here it's random on Ethereum, but it can be like any unbiasable source of randomness. And it uses this source of randomness called random to randomly sample M signatures, right? So if you say that you have 200 signatures, it will randomly sample maybe 20 or 25 of them and say, okay, you claim you have 200 signatures. Give me the 5th, 22nd, 34th, and 47th signature, right? So instead of verifying every single one of them, it uses an unbiasable randomness to only pick a few signatures that it wants to verify, right? And then the relayer then gathers exactly those M signatures that the random sampling on the smart contract asked it for and sends over exactly those M signatures. And the smart contracts just verifies those, right? But if you notice, there is like some probabilistic nature to the soundness of this argument, right? So what we get is not deterministic soundness, but probabilistic soundness, in the sense that this M, that is how many signatures it has randomly sampled, is the security parameter of the protocol, right? And the probability that a light client gets duped is 1 by 2 to the power M. It's quite simple to see here, because like there is 1 in 2 to the power M chances that it always chooses a malicious validator in the claim that had been made, right? So the crux of the analysis over here is to basically, find an M such that it is efficient, but also the whole protocol is secure, right? So let's. So the main component of the security analysis here is to derive M, like the number of signatures that are randomly sampled by the smart contract, to ensure it's both secure and efficient, right? And how would we go about this? Crypto economic arguments to our rescue, right? We believe that all players are rational over here. So we do a crypto economic analysis, and the core idea here is that if some validators attempt to attack or like try to randomly like create try to dupe the light client, what they want is that their expected value of the attack is still positive, right? That they gain out of this attack. And here, this is an equation which describes the expected value of the attack. Over here, let me just maybe also show what the parameters are, right? This is like a very simple expectation, right? So you have the probability of a successful attack, that is like the light client is duped, is 1 by 2 power M. And we assume that if something like this happens, then the overall value of the attack is like the market cap of DOT, like the maximum possible attack value. And in case he gets caught, then he is going to be slashed, right? So 1 minus p is the probability that he is going to get caught. And if he gets caught, he loses the slash. This is like the minimum slashing amount for a validator, right? And note that, we only have slash on validators here. So there is like the relayers don't have any skin in the game. So we finally have to track down the validator who made the malicious signature, right? So this kind of like looks like we've come up with the right M, which explains and ensures that the bridge is safe and efficient, right? But hang on, like there are a lot of details that are missing in this simple analysis, right? So there are like two main issues in the slide that I showed you before. And the main point here is that we assume that the protocol is one shot, right? But actually, it is interactive. There is like some delays, yeah, and so on. So there are like two main issues. One of them is the source of randomness that Ethereum smart contract uses is biasable, right? So RANDAO is biasable. It is known and already known in literature that it is biasable, but we do a more thorough and tailor-made analysis for our particular use case, and it doesn't look good. So we have to kind of somehow negate that bias in the randomness. And the other thing is there can be like concurrency issues that can be exploited to increase the probability of a successful attack, which I'll get to in a minute, right? So let's first look at the RANDAO biasability issue, right? So Ethereum uses a mechanism called RANDAO, where every block producer somehow adds his own bit of randomness into a stream of randomness. So every time a block producer produces a block, he adds his own like bit of randomness into this pool of randomness, right? And what is already known is something called like the last revealer attack, right? So an Ethereum block producer can skip authoring a block to bias that one bit of randomness. So if he produces the block, he knows the random number is going to be, let's say, even. But if he doesn't produce the block, he knows that it's going to be odd. Then he can make sure that whatever the randomness number is being generated is odd or even, right? So he gets that one bit of bias that he can create in the random number. And we have seen that this randomness can slowly build over time, right? So what we do is that we perform like a Markov chain analysis to quantify this bias, like how probable or like how long is basically the tail, that is how many bits of bias that can a set of malicious validators on Ethereum like create to bias the random number here, right? And yeah, we kind of went over and above the already existing literature and found even more issues with the RANDAO process. But the solution here is quite simple, right? What we do is we just add extra signature checks. We just increase our security parameter to negate this bias, right? And assuming a two-third honesty on Ethereum, like two-thirds of the validators are honest on Ethereum, which is like a very like basic assumption to make, we see that we have to add like 10 extra signature checks to negate the bias that the malicious validators can make. So yeah, here there is a problem, but the solution is pretty straightforward. The second issue is very subtle. It comes in like some form of concurrency here, right? So let's say there is like one malicious validator, right? So he signs a malicious block and sends it over to the relayer, through the relayer to the light client, and he has some stake associated with him, right? So if he got caught, his stake would be slashed, basically. But the point that we notice over here is that only validators get slashed, and usually it takes some delay, like a delay of 2 epochs or something to slash the malicious behavior. So by the time he signed a malicious block until the time he finally gets slashed, there is a delay of certain time, right? And this can be exploited by malicious validators. So what they can do is, during that delay, they can just spin multiple relayers and try to dupe the light client. And what happens over here is that, yeah, like a concrete situation I have described over here, that you spawn multiple relayers, but using the same malicious signature. And while the same, so basically what's happening is that the validator is getting multiple roll at the dice, right? So multiple chances of looking for a favorable randomness, but it's the same stake that is, yeah, like that is under the possibility of being slashed, right? So he can roll multiple dice without like incurring extra repercussions. And this is not good, right? Because every validator now can just like keep bombarding the light client within that period of like the malicious behavior while having the same stake that is slashable, right? So we have to find a way to work around this, right? And the solution that we came up with is called like dynamic sampling. So the idea here is that we make the smart contract even smarter in some way, right? So the the idea here is that like you dynamically increase the security parameter when you know that an attack is going to take place. So if you see that a lot of like relayers are sending you messages, then you increase the security parameter, right? And you increase the security parameter, but this increase of security parameter is logarithmic in the number of messages being sent, right? So in a way, this is good because people cannot like kind of try to grief you by just like sending large amount of like requests just to increase your security parameter, right? So the key features are that like the signature checks increase only when an attack is launched or like an attack is detected. And with this approach, there is no limit on the number of relayers and no extra trust assumptions, right? So you can still have a lot of relayers, but if they all start sending you at the same time, you just increase the security parameter. And this is the point I already briefly mentioned, that can relayers start spamming just to increase the security parameter? In principle, they can, but it's going to be super expensive for them, right? And again, since we assume rational behavior, they will, like such a griefing attack is not possible. So to conclude, right, I didn't give you like the final equation, but from this analysis, we figured out that like the security parameter depends on all of these variables, right? Like the honesty assumption on Ethereum, the honesty assumption on Polkadot, the number of validators, like the maximum possible attack value, like the minimum validator stake that a validator will lose if he is like signing a malicious block, like the slashing rate, which we have set to 50% right now because there is no reason for a validator to sign a malicious beefy block because of networking issues, right? And then, of course, like issues with the RANDAO, which is running on Ethereum, right? And finally, the last one is the one which is related to the dynamic sampling, which increases if like the same validator signatures are being used by relayers to make multiple requests to the light client, right? So basically, to conclude, like this analysis was more on like the security front of things, but in the end, it also ended up like increasing like the efficiency of the bridge, right? Because by multiple folds, because now we exactly know what are like the trust assumptions that we are making, and how changing this one security parameter really reduces the cost of running the bridge.
Awesome.
That's it. Thank you.
All right. You guys have any question? We have time for a few questions here. Any question? Yes.
Yeah.
Here's the mic.
Thank you very much. Did the merge change the manipulatability of RANDAO? Because now you no longer have to hit a certain hash, so I assume you can manipulate more fields.
Yes. So actually, the change from Ethereum moving from proof of work to proof of stake added a lot more signature checks. So the RANDAO biasability, or like the randomness biasability, was lower when it was proof of work Ethereum, but with proof of stake, you have all these like last revealer attacks which increase the bias, and which we had to account for. So it increased the number of signature checks by like 4 or 5.
Right. Yes. Let's pass the mic so people can hear it too.
Sorry, just to add to that, there's also another step which probably wasn't included here to simplify the presentation, where we force relayers to wait like 32 slots in the future before they can actually claim the RANDAO value, and that also reduces the possibility of them predicting RANDAO. It's. I'm not sure what. I know it's like 25 minutes in the
Yeah.
beefy contact, which is like 125 slots or something. No, so I was wrong. It's not
128 slots.
128.
Yeah, somewhere around that. Yeah.
All right. Yes. Okay, so